30 years, half of his life. And half of my life too. And he has been in close contact with us since then. Very frequently he visits this place. I think I consider Alberta as part of the institution. And I think vice versa, according to what he told to me before. In particular, he was the advisor to George Lubelli, who is our colleague here. And loves the kind of subject he's going to speak about today, which is the interaction between medical imaging and mathematics.
Muito obrigado. Jaco already gave half of my thank you speech, giving out all these dates, so I'll be a little bit brief. This may be on focus, maybe not. So first I wanted to congratulate, it is true, I came here in 1973 for the first time. I owe this to Jürgen Moser, who told me about Jaco and about this interesting place. And I came, it was a different location. I mean, it was this Rua Luis de Camões, the great Portuguese poet, a long time ago. And I truly feel this as my own place. So I'm happy to welcome Jaco to this place, okay? So thank you for all the past visits and hopefully all the future ones. In fact, today I thought of going to show a movie. I wasn't quite sure that you had the equipment, but if you invite me again, I'll bring a movie. Apt for everyone. I mean, it's a proper movie. So once I start into the talk, you may doubt that I have a plan, but I actually do have a plan. And first, I'm going to try to tell you everything that I want to say in about 5 transparencies. And then depending, I'll count how many people are still awake. And I may give some of the details, okay? Now, the subject is, in fact, the interaction between mathematics and medical imaging. I don't want to spend too much time showing images, so I'll just put one up here. I hope it shows. I mean, everyone knows and has heard tons of times that mathematics has had a tremendous impact in diagnostic medicine and even more recently in interventional medicine. So this is not an application that has to be sold in a very difficult way. What I really want to talk about is sort of the other side of the road. So I have here, I'm trying to adjust to this limit that I see here. I have in one, this is one of the 5 slides that ought to summarize what I want to talk about. I mean, I'll go into more details in a moment. There are 2 basic things that photons, no matter what the energy is, have to do when they go through human tissue. They get absorbed, and they may experience some scattering. Absorption is you simply don't make it through, you die somewhere along the way. Scattering is, for our practical purposes today, you change direction. You survive, but you change direction before you go between the source and a detector. Now, I split the way that I look at medical imaging essentially in 2 halves. Up here, I have essentially the case of X-ray or MRI or PET scanning. If I knew how to point, there we go. In these cases, I drew a straight line here to indicate that we ignore scattering. And the reason for that is that, relatively speaking, the energy of the X-rays, let's say, is high enough that you can assume, it's not quite true, but you can assume that there is no scattering. So there is some unknown function rho of x, which is the attenuation or absorption density, and you try to recover that function from lots of line integrals. That's a very classical thing. So I wrote linear here. The point is that the equations in which this function gets trapped in are linear equations, okay? Linear has to do with the fact that you have ignored scattering. Now this has to do with what I call here high energy. There are no medical doctors in the audience, I hope, so I can use the word. I don't mean really high, I mean relatively high, higher than the case that I'm going to be talking about is essentially what goes under the name of diffuse tomography or optical tomography. In this case, you do have both things, and you're trying to image both of them. At every point, there are certain properties that vary from point to point, which have to do with these two things, and they have some diagnostic value, and you would like to image that. Now, the basic physics is entirely different. From a source here, different photons will do different funny things. It looks like the Brownian motion that Jack Newman had earlier today. It almost looks like a web, as Phil Griffiths had yesterday. So you have to surround the object with detectors all the way around, even if you don't move the source position. I mean, the actual path here is through, let's say, the geodesics of some unknown metric, if you want to put it like that. Now, that would lead to nonlinear equations. So that's the basic difference. And let me compare these two things side by side. I'm calling linear tomography what is around already. The one, let's say, X-ray tomography. Whereas the other one I want to call nonlinear tomography. In this case, I mentioned already, the energy is sort of high. Here is much, much lower. Here is below the energy of visible light. So this is truly low energy. Here scattering is ignored. Here scattering is a dominating phenomenon. I would say that this is mostly solved. I mean, from the point of view of math, I don't expect any great new developments to come. I wish I were wrong. Maybe I'll be wrong. But this is nothing too hot in some sense. Whereas here, I would say the problem is completely unsolved. In the linear case, the model is very well understood. It's this model that I drew in the earlier transparency. It's a model that essentially goes back all the way to Poisson. The way in which you obtain the measurements is to assume that as the photon travels, in each little segment, say this little delta x somewhere along the way here, that delta x over there, the probability of surviving as you travel through is given by, say, 1 minus this attenuation density. You then multiply all the things, and in the limit you get the exponential of some integral. Okay, so nobody has competing models in the linear case. In the nonlinear situation, the story is entirely different. There are many, many different models. Each one of them is wrong in some way or the other. Either you start from the full wave equation. I mean, there is going to be some linear equation here. I don't mean the nonlinear wave equation. What is nonlinear here is the inverse problem that comes about. You're trying to determine coefficients in the equation from input-output observations. Other people use the diffuse approximation, the transport equation. I'm going to be talking today about a very, very simple-minded, discretized, totally discretized in time and space model. And this, as you will see, will fail to reflect some of the physics of the other ones. But here, at least, we can do a lot of interesting mathematics. And hopefully, some of that can be done in that case, too. I'll show you later 1 or 2 pictures. This is my own personal view. Maybe I'm wrong. Here, I think the stories are entirely different. I think that if there are going to be interesting developments, that means a machine that is sitting by the side of a patient in the hospital. That's what I mean by a development. I don't mean just proving a theorem. You have to prove a theorem first. But those developments, if they happen, could be driven by mathematics. So I wrote here, just to be silly, 12th century algebraic geometry. Maybe it's more 17th, 18th century algebraic geometry. I'll show you some horrible equations in a moment. So that's the second of my 5 transparencies. So let me concentrate now in this very, very simple-minded, discretized model. And I thank Jack Newman for his talk today, because I can then go faster here. I'll use some of his same words. So I'll have a discretized model. Imagine you're a photon. If you're a photon, you're in one of these positions. Notice that I have here discretized phase space. Not only the position matters, but the direction in which you're moving matters. That's why a state for me is an actual arrow. And there are going to be 3 kinds of states here. The so-called incoming states, they are drawn here in blue. I didn't want to draw all of them. In each one of these pixels, you should draw an incoming blue arrow. So I drew a few of them. Then there are going to be outgoing states that correspond to detector positions. Again, they should have 1 all the way around on each one of these pixels. And then there are lots and lots of these so-called hidden states, which are inside the body. Now, the picture that I have in mind, each one of these arrows is a state in a Markov chain with a finite number of states. Time is discrete also, so it takes 1 unit of time per elementary transition, and there are the 3 kinds of states that I mentioned over here. Now, the inverse problem that we will have to solve is that I'm going to have an unknown 1-step transition probability matrix P. That is, in 1 step, let's concentrate here for a second. Suppose you are sitting in this 1 state at time 10, then several things can happen to you. In fact, 5 different things can happen to you. You could go in 1 step out of this pixel going south, or you could go continue in the same direction going east that way. I haven't drawn it here. Or you could go north, or you could go backwards. Maybe I should draw them right now. So from that particular thing, you could go in this direction, or in that one, or in that, or in that. So the 1-step transition probability matrix is a very local matrix. You only go to your nearest neighbors in some appropriate sense. I will not assume that these numbers necessarily add up to 1. So you could die in this pixel, and that's what models absorption. Okay? Now, this is going to be the eventual story, and the problem will be to look at the so-called input-output data and find from there P, if you can. What I mean by input-output data is probably something like this. I take an incoming state, this one, say, and that outgoing state. In terms of this unknown P, I write down the probability that eventually, I don't care how many steps, I will go from this incoming position to that outgoing one. That's my data. I do this now for every possible source detector pair, and I call that my data, and the question is, can I recover from there the matrix P? I may be willing to add a little bit of extra information. I may want to consider the following random variable, the time that it took to go from here to there. That's a random variable. Realize there are an infinite number of paths going around here. You can meander all your way around before you get out, if you get out. And I may want to consider the time that it took for this transition as piece of data, maybe the first moment of that, or the second moment, something like that. And this is nowadays possible with very fancy technology. You can measure the time of flight. So I'm coming to the end of my 5 transparencies. Let me tell you what will be the punchline, and then we'll vote and see if we want to see the details, okay? So this is the punchline. I claim, well, I wasn't very clear. Remember, I had these 2 models, the linear one and the nonlinear one. The linear one is the one that I would call the less realistic one, the one that you could use in the case of X-rays, but you could not use in the case of low energies. So the punchline will be this: a more realistic version of the imaging problem using scattering, I claim, leads to a very general set of horribly nonlinear polynomial equations in many, I should have written many, many, many variables. We will see in a small example how many they are. And yet, the following thing happens. I claim that this system, this is a huge system of equations, say 500 equations, in 700 unknowns, something like that, can be solved exactly in the sense that you solve using Cramer's rule for linear equations. That's what I mean by solving exactly. I don't use the word iterations. I don't solve in any approximate fashion. And what I find absolutely amazing is that in some sense that I'll make precise in the next transparency, they give you a better situation than the corresponding linear approximation. That is, the proportion of things that you can find from your data is better if you measure the ratio in the fully nonlinear case than in the linear one. The problem that I would like to pose, and this has to do with the title of the talk, the interactions between math and medical imaging, I think this gives rise to a very important, for me at least, mathematical problem, which is to understand how come this is true. I mean, if you are semi-reasonable, you must assume by now that I'm totally crazy, that this cannot possibly be true, and maybe you're right. I hope not. So I think there is a lot of math to be done. So let me, now this is my last of the first 5. I have some numbers here that will illustrate what it is that I'm talking about. I will come back to these numbers in a moment. Say, the physics will change. First, we are dealing with a linear case. Then we're going to be dealing with a case when you allow photon count to simply measure the probability that a photon that started here eventually landed over there, summing over all these Feynman diagrams, whatever name you want to use for that, okay? Then you may consider the case where not only you do photon count, but you also use some information about time of flight, so the expected value, say, of the time that it took you to go from one source to one detector. In these two cases, the equations are very nonlinear. Before they were linear. And then finally, I have a comparison here between dimension 2, which is the only thing I'm going to show today, and the one that one has to do, which I have done, but you don't have the patience to see, which is dimension 3. This is the relevant one. Photons don't like to stay on a plane any more than they like to stay on a line if they have low energy. So let me walk you through these numbers rather quickly. We will see in a moment that in the simplest of all cases, you have 4 unknowns, you have 4 equations. So you would say rather quickly, well, I've solved everything. The equations are linear. You soon discover that there is a null space, and you can only solve for 3 out of the 4. If you go now and allow for scattering, this is the case where you rule out scattering from scratch. Then in the same silly 2x2 case, you will have 64 unknowns, 64 equations. These are now, and I'll show you one, fully messy, quite messy, but no approximations. And you can solve exactly for 48 out of the 64 unknowns. And the proportion is again 3/4. If you are in the 3-dimensional case, the numbers get a little bit better, in fact. Okay, I mean, here is a drop down. I realize that 5/6 is less than 7/8. But by the time that you use time of flight, you're actually in great shape. In the case, when you use time of flight, in dimension 2, there are the same 64 unknowns. Now you have twice as many equations, and that allows you to solve, in this case, 56 out of 64. The rest is a gauge that cannot be determined no matter what you do. So there is a certain proportion of things that you cannot determine. That will only come eventually if you make some physical assumption. If you say, I should have isotropy, or I should have microscopic reversibility, meaning the chance of going from here to there is the same as going that way. If you start making those, then you can solve for everything. But in general, using just math, this is the best you can do. And you can do that in terms of very explicit formulas. So I'll actually come back at the end and show you the typical formula that has to do with this. And in the case of dimension 3, the situation is the best. So that's what I'm really talking about. Now, in the interest of truth in advertisement, I should say that I don't understand at all how can this happen. I mean, this is just the result of an obsession going year after year and solving these equations. I wish I knew what is behind that. I mean, you cannot solve nonlinear equations exactly with explicit formulas unless something very special happens. Okay, so now, should we vote? Should I go on? We can all go to the beach now. What time is the next talk? Now?
I feel like we want to go on.
On to the beach. Okay, I mentioned something. I don't want to give anyone the impression that all the work in linear tomography is dead. So let me take 1 minute to talk about that. You may have seen pictures like this. This is the way in which data is normally taken these days. You have here the head and the shoulders of a patient seen from the front, and you have a gantry with an X-ray tube that rotates around. The X-rays come on a fan, and you measure the line integrals that way. Just to give you an idea, I mean, this machine has been around for a while. If you're very young, you've never been inside one of them. As you age, that's another quote from Chuck today, you will change. Oh, this is too dark. But that's all that I can do. Well, maybe the next one is a little bit better. I'm not sure. Is there something that it's not really such a big deal. Anyway, what I was trying to show there, you may see there is a human there holding with his hands, it's a man, believe me.
Not you.
Not me. Now, a flat detector here. See, this technology started around 71, 72. Detectors were just a unit at a time, so you were measuring one line integral at a time. Now there are these amazingly large detectors produced by all sort of companies, and a lot of linear mathematics will have to be developed to take advantage of that. So I'm not saying that everything is finished, but I'm saying that the progress will be dictated because of somebody building a gadget. So I have to show some formulas. Well, in fact, I'll show you many more formulas later, but let's go back to the classical picture traditionally attributed to Radon, another one of these lies that we propagate all the time. Radon was not the first guy who did this. It was Hendrik Lorentz, the Dutch physicist. He didn't do the case of the plane, in all fairness. He did the case of R3. R3 is much easier than R2. But Lorentz knew, and Radon knew also, that if you have an object in dimension 2 and you measure all the line integrals, let me call this function f of x. That's what I was calling rho before. That's the unknown function. You measure the integrals. Well, going back to this Poisson model, there is a reason why I keep saying Poisson. In the model that I'm going to be talking about, this probabilistic model with the Markov chain, somebody will say, well, this guy is even crazier than I thought. What is probability doing in this subject? I want to say that even in the ordinary tomography case, there is probability already here. I mean, you don't derive this formula unless you believe in the Poisson model, okay? So the intensity of the source is connected with the one of the detector by means of this formula, and this formula is nothing but passing to the limit with this product of 1 minus f sub I, okay? There is, in that case, a very explicit formula. I mean, these integrals, you take the ratio, you take the log, and so on. So your data consists of these integrals, and then there is this beautiful formula of, let's say, Lorentz dash Radon and lots of other people. This formula has been reproved by lots of other people later, that from the data, you stick it in here, there is some linear operation, it doesn't matter what it is, and it gives you the unknown thing, okay? So I would like to find a formula like that even when you have a nonlinear problem. So to do that, oh yeah, one of the earlier papers on this business, I didn't really know that Jacob was going to remember George Subeli in this context, but way back in, I wish this were 1890, then we would get in line for, but it's actually 1990. Anyway, we wrote a paper in Science. There was a little company headed by Singer, that's why his name is out of alphabetical order, where we actually proposed not an exact formula at all. We simply proposed some iteration method of solving this huge system of nonlinear equations, and George Subeli, who was, as Jacob had mentioned, a product of this place and back in this place, you should be very proud of him, was part of that effort. I want to mention, the group that is actually, in my view, leading the battle here, and there are very important medical issues here. One doesn't do optical tomography just because it's difficult. Mathematicians may want to do that, but there are real people out there too. I'll give the credit for this picture in a moment. And I'm not saying that this optical tomography will replace X-ray tomography. That would be crazy. You have to select your targets very carefully. So there are two obvious areas where this is being pushed. In a neonatal clinic, you don't want to use X-rays. You're talking about premature babies, 5 months into gestation. And here is, if you look very close, This is actually just a phantom. I mean, this is not a real baby, but it's supposed here is the head. If you look very carefully, you see the nose and all the rest. And there is a ring of detectors around here. And you inject light at one point and you collect it at the other points. And this is done in order to determine the amount of oxygen in the blood. If the level is very, very low, then you realize that this premature baby may not be a good prospect. The decision is what to do, okay? What they normally do in the hospitals today is they take blood from a toe to decide how much oxygen is in the brain. Now, if they were doing this on a patient of my size, that would be totally crazy. For a baby which is about the length of my hand, it's not so bad, but this certainly would be much better. The other obvious application is repeated mammographies. You wouldn't like to do repeated mammographies using X-rays every 30 days, but using optical tomography, well, is much less energy than the one you get when you put your hand under the light. Okay, so this is the driving force behind this, and I stole or got as a gift the previous transparency from this group. These are my friends in London, Simon Arridge. You may want to see a fantastic review paper that Simon wrote for the best journal in the world. I hope you all know what that is. It's the one of which I'm the editor. It's called Inverse Problems. If you want to learn about the subject, take a look at Simon Arridge's recent review paper. This gives you a very, very good introduction to the subject. Okay, so what I'm going to do now is abandon all pretense of physical reality and talk about this very simple mathematical model. So the model is going to be a 2x2 object in dimension 2. And I've drawn here the same. This is smaller than the one that I've drawn before. And this is the one that I'm going to be talking about. The one that I can actually solve is this one. So there are 8 incoming states drawn here in blue, 8 outgoing states drawn here in red, and 8 hidden ones. All right? Now, first I want to revisit basic classical linear tomography within this picture. I mean, this is now math. So I'm going to take certain licenses in terms of being practical. So I have here what I call a discrete model of tomography with absorption and no scattering. This is just a very special case of what I was talking about before. The point now is that I'm going to assume the following. I'm going to assume, for instance, let me come back to this, that if I happen to be in state 1 initially, in one step only 2 things can happen to me. Either I die in this pixel or I come out. But if I come out, I cannot change direction. I have to go into hidden state 7. Once I get here, if I get here, either I die here or I go to the detector over there. Okay? So that's the simplification that I'm making now. And later on, I'm going to remove that simplification. Well, if you think for a moment, there are only 4 unknowns now, and they are the chances that you will get killed here or there or there or there. Those are the things that I call rho sub ij in the next transparency. So starting from scratch, I have these unknown absorption probabilities. The traditional way, just introduce some new variables. And then, if you think for a moment, you see how come you get your linear equations. This is a one transparency short course in linear tomography. The one piece of data is the probability that you go from a detector up here on the left top to the same detector at the same height on the right. You have to survive the first pixel and also the second one. You multiply these 2 guys, but in that notation, that is the sum. Likewise, you go in these other 2 directions. People that know the business will realize that this is tomography before anybody thought of rotating the gantry. I'm not doing that. This is just 2 views, but it's good for my purpose. And you get these 4 equations in 4 unknowns. Unfortunately, there is a kernel. That particular guy is in the kernel, and you can only solve for 3 out of 4. So that fills in part of that table. Now, in a moment, the equations will become horrendous. So let me take a step. I draw the picture again, and now what I was calling 1 minus rho 1, 1, in general, will be denoted by E11E. What does that mean? It means that I was coming from towards the east, went through pixel 1, 1, and came out east. Now, in this very simple model, this is also the probability of having come into this pixel here going south, that is from the incoming direction 8, and coming out with the hidden direction 2, and likewise all these other ways. You can go from this 1 to that 8, or finally from this 8 to this 1. That's the west 1, 1, 1. So you see, in the linear case, many of these variables that in a moment will be totally free have been compromised. We have taken some submanifold and made them all equal. Okay? So using that notation, if you're still with me, I'm going to now allow for very general transition probabilities. The transition probability is going to be a huge matrix. There isn't enough room to put that in one transparency. So remember, this is the state of states. There are 24 states. The states are broken up naturally into 3 different classes: incoming one, outgoing ones, and hidden ones. So I draw here, for instance, a block of that big matrix that contains only the one-step transition probabilities between incoming and outgoing directions. Well, looking here, it looks more or less like a discrete Laplacian. I mean, there is something local because I don't want in one step a photon to jump too far. So each one of these 16 non-zero numbers are now unknowns. See, here you don't recognize any of the ones that I had before, because in the case with no scattering, there is no way to go in one step from an incoming to an outgoing. You have to go at least through 2 of these pixels. Here is another block, the probability of going in one step from an incoming to a hidden one. Again, these ones you don't recognize. Maybe, well, I'm just trying to show you that there are 16 times 4 of these unknowns, and you believe me that there are 64 of them, so I hope you counted. Very good. So now I'm going to do the following thing. I want to, maybe I should make a statement here. I mean, the model that I'm going to use, that I have been talking about for the last 3 or 4 or 5 minutes, is very discretized. It may have nothing to do with the real physical problem. I grant you that. But the power of mathematics is that once you formulate, and if you can solve it, you may be able to use it for something else. So to make that possible, I want to draw everything as part of the subject that I would like to call network tomography. So the model that we're looking at, remember the states had certain labels. There were some blue ones. So now I simply draw a dot instead of an arrow, and I indicate an edge between 2 states if you can go from one to the other in one step. So here is the full graph with all the corresponding unknowns in the case of linear tomography. The question is, from the input-output relation, which is given any one of these, take one of these and take another one, compute the probability of eventually going from here to there. Well, that's 0, because there is no way of going from here to there. Just look, follow the arrows. You can only go from here to that one. From here, you can only go to that one. This is the graph theoretical picture in the case of tomography without scattering. Okay? And remember, the number was, you can solve for 3 equations out of 4. So you can ask the question, how do things get complicated or not as you allow these arbitrary transitions? And this is the graph. That's what you get. I mean, I can almost show the whole thing. The bottom is missing, but I mean, if you look very carefully, see, now all of a sudden, because I allow scattering, it is possible, you have the old things, but now you have many, many more. Eh? And this is a really horrible mess. attached to each one of these edges, there is an unknown. There are 64 of them, and that's what I'm trying to solve for. So if you look at this graph, it's completely non-planar, and it has lots of cycles, because you can meander all your way around here from some hidden states, and you can go from any incoming state to any outgoing state with an arbitrary number of steps, maybe 2 steps, maybe 3, maybe 5, maybe 27, and you have to add over all of that. Okay, so that's the graph. So there may be room somewhere to use some of these mathematics to solve an inverse problem in this thing that I like to call network tomography. So that's the same network drawn a little bit better. I mean, I don't know, it's not much better, but it's exactly the same network. It's a real mess. If somebody knows how to draw graphs like these with appropriate software very fast, please talk to me after. And you start drawing these, and pretty soon you have triple intersections. It's a real mess. It would be nice to do this on the fly and connect these with some symbol manipulator. Just in case I forget to say this, I've used extensively things like maxima, but you can use mathematic or other things. So you may want to know where is this input-output matrix. I'm supposed to stop at 3, I presume? Okay. I will, maybe even earlier. So here is an explicit formula for what I call the input-output matrix. This is an 8 by 8 matrix in our case. For each incoming state and each outgoing state, this matrix, which is obtained explicitly by this formula here, in terms of these blocks of the matrix P, gives you the probability of going from an arbitrary incoming state to an arbitrary outgoing state, expressed as a rational function in these unknowns. The rational thing comes because of this inverse that you have to take. This formula is either very deep or very trivial, assuming there is a difference between these two concepts. You can call it the Lippmann-Schwinger formula, you can call it the Dyson formula, or you can do 2 by 2 linear algebra and derive it yourself. I mean, if you use the Markov property, it's trivial to check that. To check that, you eliminate, you're there. Okay? So that's the formula. Now, this is not the formula that I'm going to use this, but this is not at all what I'm interested in. I'm interested in going back, in going from here to these pieces. This will be the solution of the direct problem if I'm measuring just the 0th order moment of the time of flight, or in other words, the probability of making it. So for notation that I will use later on, the thing that I'm calling there QIO will be called QIO super 0, meaning the moment of order 0. I will be using the moment of order 1. Now the formula doesn't tell you too much, so I just wanted to show you one entry. So the entry is, as I say, a rational function of these unknowns. So there it starts. And it continues, and it doesn't fit. This is just the numerator. It keeps on going. Believe me, I hope you notice every single term carefully. Okay? And it's almost finished now. So up to here is the end of one of the numerators. Notice these are highly nonlinear equations in a huge number of unknowns. Here I'm showing the denominator of the same term. So these are not things that you solve by hand. In fact, you don't even copy by hand because you're certainly going to make a mistake when you do that. So they are really horrible things. Okay. Maybe what I want to do now is the following. Skip over some of the details. I mean, if I show you all the details, you're going to be absolutely even more revolted. Let me tell you what happens. There is an explicit formula for the first moment of time of flight, and that's what I indicate with the super 1 here, is given by this rather nice, simple formula. It's the sum of the input-output, I mean the photon count that I had before, plus this term, only that has a -2 here. So what I propose to do is I'm going to use as data this guy, the moment of order 0, and this guy. Of course, using this is equivalent to using that thing. That's the difference. So I relabel things. I'm going to call that guy. My data will consist of moment of order 0 and this difference between the moment of order 1 and of order 0. I'm going to assume that all that is known to me. It's a horrible set of nonlinear equations where all these unknowns enter. And since I really would like to finish early, I'm going to skip and skip and skip and come to the punchline. Here is a formula. Maybe to understand this formula, it may be better to go back to some of this initial drawing. So I'm going to show you the following thing. Remember, that's where we started. Now assume that I'm allowing all possible transitions. I'm going to show you an explicit formula for the probability of going in one step from this incoming state to that outgoing state. So this will be called PIO88. Turns out, so this is going to be given in terms of the data. All right? I just chose to show one of them. So here it is. This PIO88, I claim, ignore that, just look here if you want. You have some, it says here, Q458238 divided by Q45 semicolon 23. What do these guys mean? You take the matrix Q and you form now, here is a 3 by 3 minor of it with these as rows and those as columns divided by this other thing, very much like Cramer's rule. But don't ask me why. This is just true because I tell you that it's true and we can prove it later if you want. Similarly, you have these 4 terms, and there are still here these unknown ratios, A15 over A1 and A16 over A2. And believe me that the formulas for those guys is in the next transparency, and now the devil is playing tricks on me, and I've lost that one. Oh, well, I lost it. Now you will never believe me. Please. It was here a moment ago. Well, I guess the devil also. Oh, here it is. So what is showing in here, all the stuff having to do with Q's is still using just moment of order 0. I said before that if I only use moment of order 0, I can solve for 48 out of the 64 equations. This is 64 unknowns. This is one for which I cannot solve. You see, the gauge is still there. This number, what I want to call the gauge later on. But if you allow me to measure the first moment of the time of flight, I get explicit formulas, for instance, for A15 over A1 and A16 over A2, which appear in the previous formula. And there are ratios, this R12, R13, and so on, R17. Those are the corresponding entries of this matrix R that came from the first moment. And the rest is all given very explicitly. So I'm essentially done. I just have to say one more thing. The matrix PIO is completely given quite explicitly in terms of these formulas. The other matrices, the PIH, PHH, and PHO, are not given except up to a gauge. There is some 8 by 8 diagonal matrix. There are 8 degrees of freedom. You can prove that there is no measurement in this model that can determine those. And the final line that I want to make is this, 2 lines. There is not a single approximation anywhere. Even if you use Maxima or Maple or Mathematica or whatever you want, I don't know, but maybe somebody will tell me better news, of any system that can solve nonlinear equations, in spite of all the claims in the literature. Great words, Grosvenor basis, singular, Macaulay, all that. Try to give to any one of those systems these equations, and if you have any luck, please tell me. The way in which we did this was by moving the equations around, we managed to reduce this horrible system of nonlinear equations to a finite number of equivalent linear problems. You do something, you stick it somewhere else, you do something, and so on. And that's the way it works out. So this is all done, of course, with the help of a symbol manipulator, but using only linear solves. That's the only thing that I think we know how to do. Even these machines, the only thing they know how to do. I find the fact that you can make this reduction a complete mystery, and I would love some help, somebody that will say, of course, look at Grassmann, Plucker, all these guys. We have looked and we have gotten something out of their work, or some of the beautiful explicit Italian work in algebraic geometry. Maybe there is a very simple reason why you can get these explicit formulas, but if somebody has any thoughts, please tell me. That's all. Thank you.
Please, some medical comments.
I should lose weight. That's a medical comment.
Please. That's for sure.
I guess you indicated that higher moments are probably not practical, but leaving that aside, they you do more.
That's the main thing. That in the higher order moments give you nothing. It is all, that's a very good point you made. If you look at Simon Ivory's article, he will say, he says, please don't ask me to measure higher order moments because I cannot do that accurately. But in fact, there is no extra information. And in dimension 3, it's the same story. At least for this very small 2x2 case. I'm sure that if you're dealing with a 4x4, say, it's natural that higher order moment should give you something. But that's a very good point. Yes?
What happens when you increase the resolution?
I get stuck. I'm already stuck here. You tell me. You do it and you tell me. No, we have papers. I should mention a number of. Sarah Patch, in particular, who was a student of mine in Berkeley and who now works for General Electric, but unfortunately she's not doing this because they think there is no money in this. We wrote some papers. I can give you more details, but it gets, I think my point of view is that it is hopeless to go beyond the 2x2 unless you understand this better. That it just gets horrible. There must be some simple explanation. Somebody should say, look, take Schwartz inequality and integration by parts, and everything falls, or something like that. Or, I don't know. Yes?
Uniqueness?
There is uniqueness up to this gauge. There is even in the linear case, remember you have 4 equations, but you can only solve for 3. So there is one variable that in principle cannot be determined unless you make some physical assumption. The same story applies in the nonlinear case. So there is uniqueness up to a very explicit gauge. I mean, I can show you papers and so on. We say these things of these, say, 64 parameters, even if you use all the higher order moments, there are 8 of those that cannot be determined just from the math. At that point, and I think that's the order of the factors here is important, my impression is it's better to do all the math, the dumb math first, and leave the physical assumptions for later. Because physical assumption means you're identifying too many variables. You're making a problem that is already messy, even more nonlinear by doing that. I think if you look at the equations, they are multilinear, by the way. In these expressions, there is not a single power higher than 1. By the time that you start making assumptions, you can give uniqueness later. But if you don't make any, I mean, if you're playing against the devil, and the devil doesn't know about isotropy, or about microscopic reversibility, or some few other standard physical assumptions, this is it. You cannot find more than this. So in that sense, you don't have uniqueness, but we have a perfectly well understood we know exactly what it is that you can give freely.
Even without a resolution?
Higher resolution gets much worse. This is the direction that Gregory is asking. I think higher, I don't know, young people like you should go higher resolution. I'm an old man. I just want to understand the 2x2. And I'm afraid I don't have enough years left. But it would be nice. Yeah.
No more comments? Or a couple of announcements. Tomorrow at noontime, we'll have a group photo for the ones that came to this second week of this celebration. And in particular, the panel speakers of this second week. And then there should be some announcement about a dinner party for next Thursday evening. Okay, let's thank Alberto.